All right, so we continue with solving our task on neetcode. So we next go to the trees. So first reboot with the root link, and a node x in this tree is named good if in the path from the root to x there are no nodes with value greater than x. We have to return the number of good nodes in the binary tree. So for example, we have such binary tree and the output is 4. Why it's 4? Because nodes in blue are good. So the root node is 3, is always a good node. And then we have a definition that a good node if in the path from root to some x there are no nodes with value greater than x, right? So, for example, we have 3. If we go to the left, we have 1. So this true then. Given a binary tree root and node x, so here node 3 in the tree is named good in the path from the root to x. There are no nodes with value greater than x. Okay, so 3, 1, it cannot be because 3 is already greater, right? Then from 1 to 3 also is not possible because 3 is greater. So we have 3 here as a separate node. We have this one. Then we have 4, 3, 4. And so 3 is always good node. Then we have 3, 4 is a maximum value in the path starting from the root. Then we have 3, 4, 5. So is a maximum value in the path. And we have 3, 1, 3 is the maximum value in the path. Root node 3. But why we cannot use, for example, 4? Because we have the path from 3 to 4, where 4, yeah, but we can have 3, 4. So what is the problem then with this case? Okay, let's check another example. So we have 3, 3, 4, and 2. And in this case, we have 3, 3, 4, and 2. We have node 3. 3, 3 is not good, okay, because 3 is higher than it, okay. So we can have 1, then 2, 3. Okay, let's try, no, not this one. Let's try, can you explain in short this question with details when the node is good? So here we have 3 nodes, right? That is good. Okay, so a node is good if in the path from the root to that node there are no nodes with value greater than that node. So we have 3, 1, 3. So root always first node. Node 4 is good because 4 is greater than 3. Node 3 is not good. No, wait, path 3, 4, 5. Path 3, 1, 3. Restart. Okay. So we can calculate like different paths to the nodes, and we can find if in this path we have like node with minimum value, so we can pass minimum value here. So from 3, for example, we can pass 3, and we check, okay, 1, is it like minimum? No. So then we cannot take this 1, because 3, it will be always the minimum node here. So we take 3, then if, for example, we take 4, so from 4 we didn't take, so we go to the left with 3. So yeah, so we check that this 3, it's actually, yeah, I'm interested in the maximum value in the node 3. 313 is actually working because it should be greater, right? So if it's equal, then it works. Okay, so I think it's quite clear for me. Let's now try to think about the flow, how it works. So first flow, how many nodes we have. So let's say that we have 10 in 3 power, so we will have 1000 nodes. Okay. What is node value? So let's say that our node value is from 0 to, let's say, 1000. Okay. We can have duplicates. And I think that's it. So let's check with the constraints. So number of nodes is greater, and we see that we can have even negative nodes. Let's bring some examples. So for example, we have 2, then we have 1, then we have 3, 4, and another one, then 2, then here, let's say that we have 0, under 0 we have -1, and here we have like 9, and let's say by 9 we have 4. So let's say we have such tree, and how it will look like. So we start always with our tree, our root, right? So when we are going through the root, it will be always our minimum. So so the first question, can this value can be less than root? No, so we never can change it. Then the question, can it be greater than node? Yes. So if node is greater than this value, then we can just add it to our result. So we can have counter. So we go in here. So 2, 1. 1, is it greater than 2? No. So we don't add it. 3, greater or equal? Yes. Yes. Add. But here and here, like also 2, we add this 2. And but it's interesting question. But here, for example, we can have 3, or we can have 4, but then we can have 3, right? So we cannot add this 3. So that's very important. We cannot add this 3. So it should be maximum then. And then also we cannot add this 2, because 4 is a maximum. So in this case, if I will calculate it, I can check the maximum value from the root. So I take 2, of course, then I take 3, then I take 4, I take 2 and 4, another 4, but I didn't take 1 and 3, because 4 is greater than these values. So in this case, I have 4 nodes. That would be the good nodes, right? I can just create this use case. For example, I can just copy 4. It will be the same. So I can create like here it would be 2. Then I have 1. From 1 I have 3. Then here I have 4. Yeah, so I have 1 and 4. 2, yes, 2, 1, 4. Then I have 3, 4. Here I have like -1 and 3. And then I have null, null, 1, and null. Then I have null and 2. Null, 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 and 2. No, also null, null, and 2. Yeah. So I have something like this. And in this case, I should get 4. So let's just return here 4 and check if it's correct expected value. Yeah, so we see that 4 is correct here. Let's try to implement our solution. So solution would be here the following. So we have a DFS function where we send the maximum value from here. So if, for example, maximum would be 4, then we change our maximum value. And we have DFS function where we send our node, we send root value, and we have some counter here, global counter, and after we do a DFS function, we actually return our counter as a result. So here it would be void DFS with a node. Here it would be max value that we actually need to change. And we can check. So if root is equal to null, we just return from here. And then we need to actually call 2 times DFS, and then we check if root value. So actually it's not root, let's call it node. If node value is less, no. Let's say like this. So for example, 1, right? So 1 we should not add. So if this node value is greater or equal to maximum, what we should do, first of all, we should increment our counter by 1, right? And then we should do like 2 DFS calls. Here we call node right, and we take a maximum between max and node value. And here we also do the same, but with node left at maximum and node value. And in this case, we should like increment our counter. So let's run it. So it's expected. And let's submit. Okay, so we're done. Let's check our previous submissions. So we see the previous submission is actually the same. So let's check another submission. And yeah, and it's also the same. It's also the same. Let's check, do we have editorial? Probably not. So here probably we have the same simple DFS function. Yeah, we just don't declare it publicly. We just implement it here. But I think that's it. So thank you so much and see you tomorrow.